ice in. Here's the situation. Okay, so you're going to pour some liquid water. Okay, you put it into like a little tray or something. You put it in the freezer at 0 degrees Celsius. Here are all the things I want you to talk to me about. Now, this is on the bottom of the back of the third page in your packet. So this guided notes you guys took yesterday, this is at the bottom of the back of those notes. This problem right here, so you can find it. It's down here at the bottom of this page right here. This situation. Okay, you're making ice, basically. I want you to tell me if that's spontaneous or not. So yes or no, and you should be able to give me a brief explanation of what it even means for something to be spontaneous. Chemically speaking, not like we spontaneously went to the mall the other, like not like that. Then talk to me about the entropy. Give me an explanation of whether the entropy increased or decreased. Then talk to me about whether this is endothermic or exothermic. A heat diagram would be wonderful here. I'll put a couple minutes on the clock. I'm going to come around and check in on it, folks. I will be asking people questions about this. I will be asking them why for their answers. Okay? And I'll be using popsicle sticks, so nobody's safe. All right. Sound good? Let's do it. Get her cooking. So there's a good amount of confusion regarding these, and I am very okay with that. Today is a practice day. In fact, I feel better about the practice days where we have some people confused, because then we have good discussion. Then we make sure we are correcting thinking and that kind of thing. The days where like no one had any questions, that actually kind of worries me a little bit. So now I'm going to be mowing people down with my popsicle sticks here. First victim will be Mary. Mary, are you with us? Can't remember if she's a chat user or not. She is a chat user, yes. Okay. Hey, Mary, can you just tell me whether this is spontaneous or not? Just a yes or no, pretty please. She says yes, and I agree. This is a spontaneous reaction. I'm going to go with a yes on that. Love it. Thank you so much. Now, I would love, let's see here, Mr. Blaze, give it a shot. Can you tell me what it means for something to be spontaneous? Like, what does that even mean in chemistry?
Either it's exothermic or it goes up in entropy.
Ooh, I totally agree with that. I love that. We'll get to that here in a second, but just what does it even mean to be spontaneous? Not what causes it. I don't know, whatever.
The process that occurs without ongoing cellular.
Yeah, okay, all right. I mean, I'm glad you got the notes. So spontaneous means like the process will basically happen without you having to do anything, okay? Now, you might start it. So like I put the water into the freezer, okay? So I started it. I lit the candle yesterday. I started it. But if you don't have to do anything from that point on and the reaction still goes down, that's spontaneous. So here, I put the water in the freezer, and then I'm all done. Okay? That's why it's spontaneous, because this will occur without me having to continuously do something. Okay? All right, pretty good, pretty good. Let me see here. Meg, I would just love for you to talk to me about the entropy of this situation.
I said that since it's going from a liquid to a solid, which freezes.
How do you know it's a liquid to a solid? What part of this tells you that?
Because water freezes.
Right, but even if you didn't know that, what if this is a chemical you didn't know? If you just had this reaction right here, how would you even know that? What in here tells you what phases you're going from? Yep. L for liquid, S for solid. Just, we're all familiar with water, so you know that already, but just in case this is some weird chemical you weren't familiar with, boom and boom, that'll help you out. Anyways, continue. So liquid, solid, what happens with the entropy? Yes, it would be quite a decrease, okay? Liquids are more disordered. They have higher entropy than solids. So we're going boom, boom. We're going backwards. That's like a 5 to a 2. So that's going to be a nice decrease in entropy. Da, 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 da. All right. Let's see here. We'll go with Mr. Kapustin. Is this endothermic or exothermic?
So we know it's spontaneous, so it has to be exothermic, less entropy.
Ooh, interesting. Okay. I like that reasoning. If this is spontaneous and it's less entropy, he knows it must be exothermic. That's a good explanation. What if, let's pretend you didn't know whether it's spontaneous or not. How else could you determine that this was exothermic? Mr. Blaze?
The heat's leaving.
Yeah, the heat's leaving. What is it? What is it? Yes, the heat's leaving the water, okay? Let's break down this heat diagram. Okay, so if I was going to go ahead and draw this, let's see here. We'll go with Mr. Ford. What is the system in this situation?
System would be the air surrounding the liquid. So
No, the system.
the liquid.
Yeah. The system itself is the liquid, okay? Again, Mr. P draws a box for all of his systems. It's not like I got a water droplet here, okay? And then the surroundings would be like the freezer and the low temperature, whatever. Where's my H going? In the system, out the system?
It's in the system going out.
Yes, okay, so here's my high temp. Okay, because think about it, that water is at room temperature when you first put it in there. Okay, so that's like 25-ish degrees. The freezer is like 0 degrees, so that's the low temp. And as Mr. Ford explained, the heat is going out of the system into the freezer. Okay? So energy is exiting the system. Again, some people are like, wait, it's exiting the system, but it's entering. So is it exit or enter? Remember, it's all about the perspective of the system. It's about the system. So energy is exiting. And so this is an exothermic process, and a few things I want to point out. Number one, the fact that something that's cold, oh, it's like a freezer, it's cold, so it must be endothermic. No. This is exothermic. So a lot of people think to themselves, oh, the flame was hot, that was exothermic, so everything hot must be exothermic and everything's cold is endothermic. No. Be careful with that. This is a cold situation, but it's exothermic. You have to focus on where the heat is going. It's exiting this system in this particular case because the system's the H, the surroundings are the L, so it's going this way. So watch out for that. I love this question for that exact reason. Because a lot of people just sort of naturally assume this is endothermic and then they get confused. Another thing to point out, so what does nature love to spread? What are the two things that nature loves to spread? Let's see here. Jasmine, are you with us?
Yeah.
Oh, sorry, my sound was a little too high. Okay, Jasmine, do you remember what are the two things that nature loves to spread from yesterday?
What it loves to spread?
Yeah, another way I can say this is, what does nature favor? What kind of reactions does nature favor?
Okay, the ones that create more entropy.
Yep, so nature loves to spread entropy. Love it. And do you remember the other one?
Reaction and processing? I don't know.
We're close. Okay, so we got the one, entropy. Let's see here. Tanner, can you help her out a little bit?
Yeah, I don't remember the other one.
He's like, yeah, I have no idea. Any of you guys in here now? Cece? Heat, right? Nature loves reactions that increase entropy and reactions that are exothermic, that is, reactions that send heat out into the universe. Does that make sense? Okay? So in this reaction, it happens spontaneously. That means it happens naturally. That means it's favored by nature. Okay? It must be either exothermic or an increase in entropy. Or it could be both. If it's both, it's definitely spontaneous. But if it's spontaneous, you know that at first, it must be at least one of the two. Okay? In another class, I sort of explained this with like basketball players, okay? If you're really tall, you're more likely to be in the NBA. That's a fact. If you're a really good shooter, you're more likely to be in the NBA. And if you're really tall and a great shooter, you probably are in the NBA. If you're really short and a bad shooter, you're like definitely not in the NBA, okay? If you're a really good shooter, but you're not that tall, you might be. If you're really tall, but not a great shooter, you're like Shaq, you might be, okay? That's how it is with exothermic and increase in entropy. If you're both, you're in the NBA. If you're neither, you're not in the NBA. If you're one of the two, it's a maybe, okay? Same thing with spontaneity, exothermic, and increase in entropy. That's kind of how it works. So yeah, this is a very good problem. I like this one. This is spontaneous because it's exothermic. The decrease in entropy is not very favorable, but the exothermic is very favorable. So this is what causes this to be spontaneous. Okay? Alrighty. So now, what is that? No. Oh, goodness. Now I want to move on to this worksheet right here. So it's going to be in a couple, and this is worksheet number 2. The little number 2 got cut off there. I want you guys to work on problems 1, 2, and 3 right now. I'm going to put a few minutes on the clock, and we'll get back to this. Okay, here we go. So, anyways, all right, so we're going to talk about these graphs here. I want absent. Oh! He's catching up on his notes. McDaniels! Can you tell me which one of these graphs is endothermic and which one's exothermic?
The first one is endothermic and the second one is exothermic.
Look at you, smart and good hard. There we go. Love it, love it, love it. Now, I did not ask you to do this, but I personally like to plot the label of reactants and products on both of these. Helps me keep everything nice and organized in my brain. Okay. So, well, can you just tell me if heat energy is going in, or entering, or exiting on this graph over here?
Wait, which graph?
The one on the left.
It's, I think it's entering.
You got it. Love it. Energy, or heat, is entering here. And so that means, Faith claps out, that the products or reactants have more energy. You got it. Let's go, baby. Okay, so remember, endothermic means entering energy. And so the amount of energy that entered is the difference between these two right here. That much energy entered, okay? Right there. Boom, boom, boom. Love it, love it, love it. And then over here we have the exact opposite, where we have energy exiting. And so the products have less energy than the reactants. And if you think about it, maybe like the candle yesterday. So the candle, let's say, had this much energy before we started to burn it. We burned it for a while. It gave off some of the energy that it had stored up in it. And the shorter candle at the end, the product, had less energy in it. And that makes sense because it was exothermic and you had some energy exit. Sweet. Okay, here we go. Let's talk about making Kool-Aid. Andrew Bracken, talk to me. Kool-Aid.
Okay, so I would say it becomes more disordered because it's going from a, I assume it's like the powder, right?
Yeah, sure.
Yeah, it's going from a solid to a liquid.
I would say increase in disorder because it's going from solid to an aqueous solution because it's getting dissolved in water, right? But everything else, really good. Love it, love it, love it. All right, let's see here. Hey, Zach, are you here?
Yeah,
Talk to me about freezing that popsicle.
it's going from liquid to solid, so it's less.
I agree. Less disordered. Again, popsicle juice or whatever it is, it's probably an aqueous solution because it's probably got like sugar and food coloring in it. So I would call that aqueous, but yeah, it's going to a solid. We're definitely getting a nice drop down there. Pretty good. Colin Howard going from molten iron into a nail.
Less disorder because it's cooling, so it's
What phases are we going to? What to what?
liquid to solid.
Yeah, you got it. Liquid solid. Definitely less disordered. And opening a can of Coke. Melania.
It's more.
I agree. Because we're going from aqueous to a gas. Remember, there's no like gas in Coke, but if you crack it open, immediately you get that gas coming off, okay? That decomposition reaction. Aqueous to gas for sure. And Gozer, Alka-Seltzer tablet and water. What's happening?
I said more because it also makes gas.
Right? You could say it's a solid to a gas, or you could say it's solid to an aqueous solution if you're talking about how some of it gets dissolved in the water there. It just depends. But yeah, love it. Okay. This next question, I hope you guys recognize that questions 2 or 3 are asking you the exact same thing. They're just a different phrasing. It's like, is this more or less disordered in 2? And in 3, it's saying, is this more or less entropy? Again, entropy means disorder. So these are actually the exact same question. So please recognize that, okay? Because I could use either phraseology on the quiz on Friday. Bree, are you here?
Yeah.
Hi, Garzini. When a liquid vaporizes, is that an increase or decrease in entropy?
Increase?
You got it. What about a gas liquefying?
Decrease?
You got it. Love it. And why don't I get Mr. Spade? Oh, wait, I think he told me he's going to be absent today. Yes, all right. So he already emailed me. We've talked. Mr. Williams. Solid melts and then solid dissolves in water.
Increase.
for a solid, yeah.
Uh-huh.
And then that'd be an increase, right?
Yes, it would. Nicely done there, Mr. Williams. Okay. Why don't you guys try this one right here? You have not done a problem like this before. Go ahead and see if you can figure this out. These are kind of odd ones. I will say that some people like to use the numbers on these types of problems. If you're a little confused at first, that's okay. A lot of people have been, but once you get it, you get it. I'll give you guys about 60 seconds on this one. Get it cooking. All right, let's go ahead and get cooking. Let's see here. CC Johnson. First one, increase, decrease, what's happening? I agree. How did you figure that out?
Well, it went from two gases to a liquid.
Okay.
Has more entropy.
Okay, so you're just sort of thinking to yourself, there's a few strategies that people use. You see gas on one side, you don't see on the other, and you're like, well, gas is kind of the trump card because that's the highest one. So if it's on one side, not the other, that probably determines your entropy right there. So that's a strategy that I think works just fine. Pretty good. Okay, so yeah, this one is a nice decrease. It is indeed. What about Mr. Ford? Can you talk to me about this one?
I said increases.
Oh yeah, how did you figure that out? What was your strategy?
First I knew that there were two aqueous solutions, so I kind of just forgot about those. So
Ooh, I love this one.
I
See,
left the solid and gas left, and then knew that increased from that.
that's the second strategy I love. If you see two of the same phase on either side of that arrow, be like, okay, so like entropy-wise, you can kind of cancel those out. Like, okay, so this sort of cancels and be like, well, solid versus the gas, I mean, the gas is getting that one every time. So that's a nice increase. Love that. Let's see here. Clark, what about this one?
Decreases
Why?
because it goes from a gas and a solid to just a solid.
Right. So you could use the sort of canceling technique that Mr. Ford did if you wanted, perhaps. Is that what you did, or did you do something different?
That was pretty much what I did.
Okay, all right. Well, that works there. And it looks like I got one more popsicle stick. Ashwag! Last one. Increases, and how did you arrive to that conclusion?
There was liquid on one side and the product had two gases.
Okay, yep. So you're saying all gas, not all gas. This has got to be higher. Here's another strategy that none of you guys happen to use on this one, which is fine. This is where the numbers can be really helpful. So if I'm looking at this, I'm like, okay, liquids, that's like a 5 plus 35. And then I got the arrow, so that's sort of dividing line. And I got a 35 plus a 35. So then if you kind of look, you can do some numbers with like, oh, which more, 40 or 70? Like, oh, it got bigger to 70. So
Where did you get those numbers?
on the notes yesterday, I sort of had a number scale that kind of goes with the entropy stuff. It's a made-up scale, but it can be helpful for this kind of thing. If you watch that part of the notes tomorrow, it'll be really straightforward. It's like a ranking system.
All gases are equal to 5.
35. So G's are 35, L's are 5s.
So you're not doing C.
Oh, no, yeah, I'm sorry. This is for D. Yeah, this is for the last one. Yep. If you watch that part of notes, is where I fill in the 5 boxes that are all parallel to each other. It's right at that part. You'll see it, and it'll make perfect sense. It's like a ranking system, though, basically. All right. Okay, we're here. Answer question 5, A, B, and C. Give me thorough responses right now. Let's kind of run through this real quick. So I'm going to go ahead and draw the heat diagram myself and then have you guys answer a couple of questions. In this situation, my system, again, those are the chemicals involved here, that would be the logs, okay? Boom, there's some logs. Congratulations, okay? Now, since they are on fire, that's going to be my high temperature. And so that means that me, over here, there's Mr. P. Oh, goodness. Why don't we redraw that? Here we go. There's Mr. P. I look like a star. Okay. Okay, I'm going to be... That's really bad drawing to me. That's bad even for me. Okay. I'm going to be the relatively low temp, and so off comes the heat this way. Okay? All right, anyways. So is heat entering or exiting the system, Mr. Howard?
It's exiting.
So this is a what reaction?
Exothermic.
You got it. Okay. All right, energy is being released. Let me see here. CC, is this increasing or decreasing entropy? Yes, why'd you say that?
Because like the solid wood is
Yep, solid wood is going to a gas. This fire is spontaneous because once you light the logs, then they'll just burn until they're out. Does that kind of make sense?
So you have to like add more logs.
Right. We've actually had a really good discussion about that. But that's adding to your system. But just think about the original system, the first 5 logs or whatever you put on there. Those will burn without you having to do anything. Does that kind of make sense? Go ahead and get those participation points. YouTube, virtual folks, you guys can get out of here. The reason why this is spontaneous, this is exothermic and an increase in entropy. And so when you have something that's exothermic and an increase, it's basically guaranteed to be spontaneous because nature loves both those things. So these work together because it's exothermic and an increase. Okay?